Hello community! Today we look at In-Context Learning Plus. So with 1 million token context length, we're gonna break through a new AI border and we talk about autonomous learning. So you know the classical scheme. We have the fine-tuning and the DPO alignment of our pre-trained little LLMs, our 70 billion free-trainable parameter models, where we take our personal or the company datasets specific to our domain knowledge, and we fine-tune it and DPO align it, those available large language models, to achieve a better task performance. And then on the other side, we have those bad corporate LLMs, like one of my subscriber calls it now. So these proprietary LLMs where we cannot go and fine tune. Or for example, I have to go and pay GPT-4 to access and fine tune and align here the model. And there's not a question, hey, is this financially the best way to do it? But with 1 million context length, what if we do not want to pay for hours and hours and hours of cloud compute? Do we have a better way? And yes, we have a better way. You remember in-context learning? Yeah, this good old friend of in-context learning. We can do this here with our fine-tuned model, but you know what? We can also do this here on those proprietary LLMs. And you remember, for example, with Google Gemini 1.5 Pro, we have now a context length of 1 million token or 1 hour of video, which is great. On the other side, on this free little pre-trained LLMs like Llama 3 here with a context length of 8,000 tokens only, this imposes here some massive limitations. Because think, if I want to give here an ICL example of a summarization, in my summarization, the text of the original article has 5,000 tokens, and the summarization is 500 tokens. How many examples can I give? 2, 3 examples, and the context length is full. Plus, yeah, I don't talk about here the actual return of this. So this is something no. And there's the reason why in the last 4 videos, when we talk about ring attention with 1 million token, infinity attention with 1 million token, this new transformer, feedback attention, memory mechanisms on a rolling shutter, and of course the next generation AI with recurrent gamma for real long context length. Now we apply this knowledge and we say, okay, sorry, but we go here with the new technology, we go here with this 1 million token. But give me 10 seconds to focus here on this 8K token sync, because Microsoft, if you look at the research literature, for example, April 18, 2024, they now start to look at the RAG system. And they say, hey, we have now our embedding models that are for 8K token max. And now we have also to work here to increase here the context length of our embedding models. And Microsoft says here they want to go from an 8K token length to, they want to push the limits to 32,000 tokens. So you see, they're working here on this side. And of course, you know, the solution here by Microsoft is the rotary position embedding. But if you look at Stanford, what they are researching currently, they are also researching about RAG, but in a complete different perspective. They say, hey, we know that everybody argues in the PR material that RAG is here to fix the hallucinations from your LLM. And they say, but what if it is exactly the other way around? What RAG provides now data that go completely contra to the internal pre-trained knowledge of our LLM. Would this not just ignite new hallucination? And they say, hey, we look here, for example, in this study here on nested financial data. And what happens now if we bring back via RAG financial data and financial data structures that have an error or go against the logical pattern trained on the LLM in the pre-training? Would this not ignite new hallucination by the LLM, given this strange RAG result that is now coming back? What will dominate, the internal knowledge of my LLM or the override here by the RAG data that are incoherent and incongruent with the training data. Fascinating topic. They also look here at medicine and law if you do this with RAG and LLM. But we are not going to talk about this in this video, maybe in a later video for my subscriber. So we focus here on the new opportunity you have with in-context learning and 1 million token length. And what we do is simple. We take now a path from the few short examples we have in context learning, and we go now to many short examples because we have 1 million token length. So if I do few short examples, normally 3 examples, 4 examples, up to maybe 9 or 10 examples. But now with this new opportunity, with new technology, by ring attention, Infinity, and on, many short are now 500 to 1,000 and several thousand examples. And you know what is amazing? If you think about RAG here, RAG can bring with this 8K context length of the embedding and all of this, maybe if you ask, hey, what is the date of Julius Caesar? When was he born? Or give me the result of the latest, I don't know, financial report. But if you ask, hey, teach me a new algorithm or show me a new causal logical reasoning path to solve a complete new problem, you run out of 8K token. So you need more space, more working memory. And this is exactly where now ICL Plus will shine over the classical RAG system. But not too much right now. Let's have a further look. So I had a burning question in my heart. Can we improve the performance of our proprietary LLMs I pay for ChatGPT Plus Super just by applying now many shots ICL? Do I need to pay for the fine-tuning? Or can I just have here one prompt with many short examples and it is much cheaper and I get maybe a better result? Is this possible? Now, remember, ICL does not change here the weight tensor structure of our LLM. It can adapt to new tasks and domains without the need for additional fine-tuning retraining. And this beautiful flexibility makes it here so precious for a dynamic environment where the system has to learn immediately new data. So to pivot quickly is crucial. This is where ICL Plus will shine. I have here an example where I have a 16 example prompt that I give to my LLM. And believe me, classical thinking is that a 16 example prompt here to an LLM is great. But you know what? The question is, can I improve the performance of my LLM without fine-tuning? Can I improve it to more than 36%? And the answer is yes, if I provide 8,000 examples in one prompt. Then the performance of my LLM, without any fine-tuning, any alignment, anything at all, will improve 36%. And 36% for an LLM is significant. So the more examples I have, what we call many-shot ICL or ICL Plus, allows now the LLM to better understand and perform a wider array of tasks, resulting in a higher accuracy and a more robust performance. And this means even across domains, I can now have a more nuanced understanding or even an advanced reasoning pattern that I can transfer in my prompt to my LLM that maybe was only partially pre-trained on this topic. Now here another example. I have a 32-shot prompt, which is beyond the normal. But I even can improve the system performance, the LLM, further, almost 20%, if I use a 2,000-shot prompt. I never thought about this, but my goodness, this is where I can achieve something amazing. And I just pay here for the prompt. So this means by providing a larger and potentially more varied set of examples at inference time, these models can now recalibrate their outputs. Remember the internal knowledge of an LLM we were talking about if you get some RAG data in. And this is now aligned more closely to the desired outcomes that I can show you in my prompt, and even in scenarios that diverge from the pre-training data sets and the pre-training knowledge of my LLM. If I have here a 4-shot prompt, which is good, and I increase it to a 512-shot prompt, my system performance goes up 21%. Just in one prompt. I am amazed by this possibility that this 1 million token context length opens up now for me and for the training. Now, this is of course task specific. So let's look at here that the task performance in percentage from 0 to 100%. And here a different task. For example, we have a summarization, we have logistic, we have question and answer, we have translation, we have mathematics, we have classification, we have code verifier. We have our classical GSM 8K benchmark. And you see, in gray, we have the classical few-shot in-context learning prompt. 5-shot, 5 examples, 1 example, already 16 examples. And in green, we have now the new many-shot, 500 shots, 800 shots. And you see, it is highly dependent on your domain that you're working with and on the task. If you have a summarization task, you think, hey, if I just go from 5 shots to 500 shots, only a 5% increase, that is not a lot off. Well, it depends on the domain data, but more about this later. But you see, 36% compared to, 5%, no, 4% here is the lowest. So this is an interesting dynamical system we want to understand. And of course, you're going to ask, hey, who is going to be so crazy to write down here domain-specific summarization patterns for 500 different examples on 500 nuances here on one particular domain? And if you look at me and say, no, but hey, wait a minute, I have a channel about AI, so maybe we can use the AI system to write this. What a coincidence. Let me give you another example here, and let's talk about the learning curve. Here you have on the x-axis the number of shots. So the more example we provide to the system, you have here the performance of the system goes up. Now, interestingly, if we have a translation task from English to Kurdish, we have an almost linear function if we give more and more translation examples to our LLM. So the more the AI learns on examples in one prompt, the better is the system performance. If you go from English to Tamil, you see, it is not really linear. Sometimes there are a little bit bumps and so, but I would say you have a continuous increase in performance if you give more and more translation example to the LLM. Isn't this nice? No fine-tuning. But careful, because if we now look at summarization task, you see that here it kind of plateaus out. There's a saturation in the learning. We're going to have a look in more detail later on. But you see, with here this dash dotted line, we have here the fine-tuned version. This is more or less constant. And if you do not do the fine-tuning, but just go with ICL plus, and you see here the number of shots from 5 to 500, you see our improvement significant, but then it plateaus out somewhere. So this means if you have a summarization, let's say 10,000 tokens is your story, and your summarization is about 500 tokens. If you as a human do this, you have a pattern how you summarize. First point is an introduction. Second point is maybe the topic introduction. Then you show, hey, what are the problems? What are the limitations? Why do we need to find better solution? So you have a certain way of thinking. And this way of thinking gets saturated after, let's say, 50 examples. After 50 examples of summarization example, with always the same pattern in the background, how to do the summarization, the system gets bored and says, hey, yeah, I know it now, really, come on, change your behavior, change your pattern. But if not, you have saturation. Also, if you have now in different models, you see this saturation effect is taking place if you stick to one method or cluster of methods or similar ways how you build your summarization. But an AI gives you the possibility to go crazy and discover new ways. And we will talk about this in a later video. But of course, if you have a maximum number of shots in blue, you ask, where is the best performance? What are the maximum number of shots I have to take? 100 examples in one prompt, 200 examples in one prompt. And this is here exactly here for quite a long list of different tasks. So you see here for Big Bench Hard with 8 tasks, a benchmark, they did 100 shot examples in one prompt, but they found that already at 50 shots, 50 examples in one prompt, this gives you already the best result. But interestingly, with a sentiment analysis, they did more than 2,000 shots. And they found, yeah, we need those because the performance of the system is still going up. And the same with translation, as I showed you. Almost a linear increase in the performance of the system. So for translation, you need all the examples you can get to learn a new language. Interestingly, for a code verifier, they found, hey, at 120 examples per prompt, we already reach here the best performance. You don't need 500 examples in a prompt. Or for a question and answer, you don't need 250 examples in a prompt. If you are in a particular domain, on a particular subset, 125 examples is good enough, so we reach the best performance shot and so on. So you see, here now, interestingly, with summarization, they show us, hey, I give 500 examples for summarization in an in-context learning plus prompt, and I need 500 because now I get here the best result with 500 examples. So if you break loose from your classical way of thinking, your classical patterns, how you do a summarization, the classical boring way of you always do as a human, and you open up to new possibilities, to new configuration, to new permutation, to new insights, to new perspectives. Yes, there's a whole new world out there. Beautiful. Now to the real interesting part of In-Context Learning Plus. They found that there are 2 ways you can do this. The first one it's called reinforced in-context learning. So you have a typical prompt. This includes few up to many human-written problems, followed by their solutions, because the AI must learn what is the way to find a solution. Now, as I told you, we will move from the human-written solution here to model-generated prompts, but yes. And second, there's now an unsupervised in-context learning, because we cannot afford to have hundreds and thousands of people somewhere on their computer in the world doing these micro jobs for us. They do not have the identical knowledge level. And. So what if we do not do the labeling of our test data? We do not do traditional learning, but we do it in a different form. And they say, hey, beautiful. Let's see if the model Only the pre-trained model has its knowledge, and we do this without supervision, unsupervised. And this particular approach is useful when large-scale labeled data is not available for cost reason or it's not available. Can we enhance the model ability to generalize from those limited instruction in an ICL prompt? And the amazing thing, yes, this blew me out of my waters. Look at this. This reinforced ICL has a structure that we know, a chain of thought rational. So we tell our GPT-4 system, hey, listen, you know what is a chain of thought? I give you maybe some examples, and in this chain of thought rationale, I want that you tackle each and every problem. Beautiful. With the unsupervised ICL, this entirely removes the rationale. So I just give the problem to the system, of course, in a domain-specific field where the system has some pre-training on. I cannot ask a question about theoretical physics if the LLM had not pre-trained on theoretical physics. So it must have the pre-training data, but not for a particular solution or a new solution. And I just say, hey, system, this is your chance to learn for some more autonomous applicability to find solution in an unsupervised ICL learning pattern. And this is absolutely interesting because here you say, okay, I give it a problem and the solution and the system must learn the solution. I understand this. But here, I tell the system just the problem and not tell the system the solution. Now, I could not imagine this to be true, and I have to tell you, it is not really true what's written here. Let's have a look at this. Example time. Reinforced, calculate the integral of x squared from 0 to 1, model generated rational, use. You know this, simple. Unsupervised is different. And now to the original cookbook. Unsupervised ICL prompt structure consists of a preamble that you will be provided questions similar to the one below, then a list of unsolved inputs or problems, so just a set of problems, and then a zero-shot instruction or a few-shot prompt with outputs for the desired output format. So now this is something I can imagine. So you see, if you read the fine print here, they tell you, hey, I have a list of unsolved problems, yeah. But at the end, I give it at least one coherent, domain-specific, zero-shot instruction. Let's look at this. I recorded in 4K, so you can read it on your 4K or 8K screen. I have here problem 1. I have a problem 2. I have a problem 3. I have a problem 4 and a problem 5. So I have a set of problems, no solution. And then I tell the system here, now I'm going to give you a series of demonstration of mathematical problem solutions. So I give it a two-shot example. Problem, solution, answer. Problem, solution, answer. But look at this. The way of, if you want, a mathematical domain here, the subdomains, they are diverse and they are not exactly here my two solutions. I just say here, hey, find the domain of the expression here, and it says here I want to have the product of matrices of A and B, the determinant. Calculate this. So I have two very general solutions to 5 problems that not all lie in the absolute identical subdomain of mathematics. But just that I tell the system, hey, with those two solutions, you could theoretically solve those 5 problems. There's a lot of knowledge from my side or from the GPT-4 side that I have 5 problems that are really solvable by combining these two mathematical ways of solving, ways of finding a solution. So you see, there's really the system challenge. Can the system come up with some original new ideas to solve a mathematical equation based on my two examples and the pre-trained knowledge? Can it find an interval of overlapping intervals so that I have here my complete answer? I find it's fascinating that this is possible, that I do not have to say problem, solution, but I say, hey, I have a lot of problems, and I'll give you your two mathematical solutions and find all my solutions to all my 5 problems. I love this idea of, I don't know, somehow now the large language model could start theoretically, maybe possible, to come up with own ideas. And the author said, hey, both reinforced and unsupervised ICL presents ways to reduce the reliance on expensive human-labeled data, my goodness, give some jobs to those poor people, and encourage the model to develop more autonomous learning capabilities. But you have to be really careful and really specific that here the subdomains really overlap, and there's at least theoretically a way that we could solve this. So this models now enhance here the ability to generalize from self-derivated patterns and directly from large amounts of unlabeled or at least minimally labeled data. So this here is a very, very precious equilibrium. And now you might say, but hey, I expect here, if I have a look here at my classical ICL in green, in teal I have now this critical, beautiful new unsupervised ICL, and in blue I have my reinforced ICL, where I have problem, solution given. And you expect blue to be always better. It is amazing. Look, we have here 2 benchmarks. The first here is Math 500. This is a high school competition level mathematic problem set. And the second here is the classical benchmark for GSM 8K, a data set of 8,500 high quality, linguistically diverse grade school math word problems. And the number of shots on the x-axis and the performance on the y-axis. This is now interesting. Just look at the green. The more example we provide in one prompt, the better the performance gets, until it reaches here its maximum at 125 shots in one prompt, and then it starts to go down. Oversaturated. Let's look at teal. Teal is our unsupervised. Suddenly, this, where I just give you one solution for a bunch of problems, is better, shows a better performance than if I would give you example and a solution to each example. How is this possible? Is this an indication that the system really found a new connectivity pattern within its weight structure, its tensor structure? Or am I just not able to find the right interpretation for this data? And you see here, even at 10 examples, we still have that our unsupervised ICL has a better performance than our reinforced ICL. Okay, we have some Streuung, but interesting. Just then later you see that now blue takes over. But again here, 250, we have another very special point where unsupervised ICL is stronger. So I find this interesting. But look at here at this other data set. Can you explain what's happening here at a 4-shot ICL? You have in green the classical ICL, uncorrelated, beautiful. Then you have a significant jump in your unsupervised ICL, amazing. But look what happened to our reinforced, to our problem solved pattern. Why the heck is it now below the normal ICL? Interesting. I don't understand this behavior of the system. And then we see, if you just look at the green, yeah, it goes up, goes up, goes up, and has a saturation. If we look now at the blue, it goes up, and yeah, kind of reaches here saturation. And teal, yeah, goes up, and maybe also a saturation. So amazing. So many amazing facts. At first, what is this behavior? How can we explain this? Why is it possible that the unsupervised ICL sometimes is even better than the reinforced ICL? And on and on and on. And you see, there are a lot of questions. And yes, for my subscriber, there are a lot of new videos where we will jump at the latest research and try to explain this, try to use this tool of ICL Plus for a better performance of our large language model. I hope it was informative. I hope you enjoyed it a little bit, and it would be great to see you in my next video. And by the way, if you're interested, this is the publication I would recommend you. Many-shot in-context learning by Google DeepMind, April 2024. And they have here a deep dive, and this is really a fascinating place to learn about the latest AI developments.